This is an example of a kind of problem you might see when it comes to this kind of stuff. And remember that what we're going to look at are just basically simple cubic, body-centered cubic, and face-centered cubic cells. So in this problem, we have aluminum has a density 2.699 grams per centimeter cubed, and the radius of an aluminum atom is 143 picometers. Let's verify that aluminum is face-centered cubic. Okay, so if aluminum is face-centered cubic, there's two things that'll tell us. One thing is that face-centered cubics have 4 atoms per cell. But the other thing is that if it's face-centered cubic, the edge of one of the cells is going to equal 4 times the radius divided by the square root of 2. So what we're going to do in this problem is we're going to start from the 4 times radius divided by square root of 2 to find edge, and then work our way over to 4 atoms per cell. We could have started with 4 atoms per cell and worked our way over to find the relationships on this side. But for this example, it's going to be easier to do it this way. So let's start with the edge equals 4 times the radius divided by square root of 2. The radius of the aluminum atom, 143 picometers. Now, a picometer is a metric prefix. Pico is 10 to the minus 12. So a picometer is 10 to the minus 12 meters. So a pico is something we'll run into once in a while. Another unit we'll run into in this section is an angstrom, and an angstrom is 10 to the minus 10 meters. We're going to run into some pretty small units. Angstrom is not technically a metric prefix, but it is used a lot in these, so just FYI. So you can see in this part of the problem, 4 times the radius, 143 picometers, divided by the square root of 2, 404 picometers. But because you can see the density is listed in grams per centimeter cubed, we better turn our picometer edge into a centimeter edge. So what you can do is take 404 picometers, multiply by 10 to the minus 12 meters per picometer to get rid of the picometers, and then you can divide by 10 to the minus 2 meters per 1 centimeter. 1 centimeter would be on top, 10 to the minus 2 on the bottom. If you combine those last two parts, you get 10 to the minus 10 centimeters per picometer, and either way is fine. But regardless, at the end of the day, the edge of our unit cell, 4.04 times 10 to the minus 8 centimeters. I do encourage you to go along with this example in your calculator so that you know how this works out and you know what's happening. Once you have the edge, because we're using these unit cells, length, width, and height are all the same. So the edge cubed will equal the volume. So if you take the 4.04 times 10 to the minus 8 centimeters and you cube it, you get a volume 6.62 times 10 to the minus 23rd centimeters cubed. And that is a really, really small volume. 1 milliliter is 1 centimeter cubed. I think a 12-ounce can of pop or beer or whatever would be 355 milliliters. This is 10 to the minus 23rd. So we're talking about super, super small volumes here because these are the little parts that make up the bulk aluminum. Pretty interesting. The density is in grams per centimeter cube. So if we multiply that by the centimeters cubed, they cancel out, and you end up with how many grams are in a unit cell. And this is also a super small number. There's not a lot of mass, grams per unit cell, because again, the volume is also so small. You can also imagine that there's going to be a lot of unit cells in one of these chunks of aluminum. We're trying to get to the point where we are figuring out the number of atoms per unit cell. So one way to do this is you can figure out the mass of just one aluminum atom. So aluminum on the periodic table, 26.98 grams per mole. And a mole, by Avogadro's number, 6.022 times 10 to the 23rd atoms. So if you take 26.98 and divide it by Avogadro's, you get the grams per atom. And that number, 4.480 times 10 to the minus 23rd. That's the mass per atom. So if you take that last number we calculated, 1.79 times 10 to the minus 22 grams per cell, and there's 4.480 times 10 to the minus 23rd grams per atom, this comes out to be 3.99 aluminum atoms per cell, and that's almost identical to 4. So we have just verified that aluminum is indeed face-centered cubic. It has 4 atoms per cell, very, very small. This is kind of a strange way to do it, but you get the idea. We're going to do more with this kind of technique in the solids and linear regression lab, which we'll do here pretty soon. And the problem set will also have some of these problems. So if this stuff is looking a little weird, just hang on to that, and I think you'll see more examples. There's other kinds of crystalline solids beyond that. There's definitely the metallic ones we've seen. There is ionic, where you have positive, negatives kind of interacting. There's covalent networks, molecular forms, lots more to do with this stuff than we've looked at so far.